Hello, and welcome to our program, Astronomy for Everyone. The topic for this month's program is the James Webb Space Telescope. And here to tell us all about it from NASA is Dr. Mathew Greenhouse. Matt, welcome to the program.
Thank you for having me.
You're very welcome. Now, could you please tell our audience a little bit about yourself and what you do at NASA?
Sure. I'm an astronomer at NASA, and I'm one of the project scientists for the James Webb Space Telescope mission. I've been working on the mission since 1997.
That's quite a while.
Yep.
Glad it's finally up, I'll bet.
Yep.
Now, we could start out with just what is the James Webb Space Telescope?
Well, if I can share my screen.
Yep.
All right.
Okay.
Okay, the JWST and space telescopes in general are our most powerful tools for looking back in time to study the fossil record of the universe. Traveling back in time is the stuff of science fiction, but looking back in time is something that we actually do, and it works as a result of the finite speed of light. If you were to look at a person seated next to you right now while you're watching this show, you are not seeing that person as they actually are. You're seeing them as they were a few nanoseconds ago, because that's how long it takes light to travel 1 meter. Now, a nanosecond is a really, really small amount of time. So that transmission delay is imperceptible to us in our daily lives. But if we look at more distant objects, the transmission delay becomes more pronounced. For example, if we were to have a magic switch that could turn off the sun, and we flip that switch, it would be 500 seconds before we knew that anything happened, because that's how long it takes light to travel from the sun to the earth. So when we look at the sun, we're not seeing it as it is, we're seeing it as it was 500 seconds ago. When we look at the closest star, we're seeing it as it was 4 years ago. If we look at the center of our galaxy, we're seeing it as it was 25,000 years ago. And so it goes as we look at more and more distant objects in space with large telescopes. We are literally seeing back in time. And that is the main objective of the Webb Space Telescope. To see back in time, we want to understand a particular aspect of the evolution of the universe. The JWST mission, the Webb Space Telescope mission, was conceived in the 1990s to connect the dots, if you will, between this famous image taken by NASA's COBE satellite of the oldest light in the universe. A Nobel Prize was awarded for this mission. And around the same time, the Hubble Space Telescope had taken what was then the deepest image that the Hubble is capable of taking. And that deep Hubble image shows us the universe when it is about 1 billion years old. And so between the COBE image, imaging the universe when it's a few hundred million years old, and the HST, which can see back to a point when the universe is 1 billion years old, between those epochs is a mysterious, poorly observed epoch known as the cosmic dark zone. And it's of great scientific interest because this is the period in the evolution of the universe when the first stars and galaxies formed. And the reason that it is poorly studied is we have not had the right type of telescope in space to observe that epoch. And that is really what the JWST mission is all about and was conceived to do. Let me go back to you at this point.
Well, it's good to know the basic premise of the mission. But where did the James Webb launch from? It wasn't here in the States, correct?
No, the James Webb, the Webb telescope is it's flying on a French rocket called the Ariane 5, and that was the part of the European Space Agency's contribution to the mission. And their launch facility is located in French Guiana, which is on the east coast of South America. And the mission, the Webb telescope, is, of course, much bigger than any rocket is in diameter. So we had to design the telescope to fold up inside the fairing of this Ariane 5 rocket. And then the unfolding of that involves lots and lots of deployable structures and release mechanisms, all of which had to work perfectly, and all of which did work perfectly. I do have a video of the launch if you would like to see that.
Sure.
So what's happening here is the rocket is inside a multi-story high vertical assembly building, and you're riding up an elevator alongside the rocket. And we're going to go up to a work platform where the JWST telescope is being attached to the rocket. And this is literally the last view of the JWST on Earth. And just soon you'll see the rocket fairing come down over the top of the JWST, the rocket assembly. It was all done in French Guiana. And then the rocket was rolled out to the launch site. And we will have a launch here.
And we have engine start. And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
And the launch was completely successful.
Terrific. Now, who partnered with the United States on this project?
Well, this project was too big for NASA to do by itself. And so we partnered with the European Space Agency and the Canadian Space Agency. The Europeans provided the launch and 1.5 science instruments. And the Canadians provided a science instrument and the fine guidance sensor that's used to point the JWST at the objects of interest.
Well, who was James Webb, the fellow that they named a telescope for?
James Webb was the administrator of NASA during the Apollo program. And beyond successfully administering the Apollo program, he is the leader that brought science to NASA, who determined in the early days of NASA that it should be a science organization. And so that's who James Webb was, and why the telescope was named after him.
Interesting. Now, what wavelengths of light will the Webb Space Telescope be observing at?
Well, the James Webb Space Telescope will observe in the infrared. We want the Webb to be able to see the early universe. And so we have to explain something about the early universe to understand why the Webb is observing in the part of the spectrum that it's designed to operate in. You've heard the statement that space is expanding. What do we mean by that? This analogy tries to explain that. What you have here is a loaf of raisin bread dough that's been set out to rise. Now imagine that you're seated on one of the raisins. What would you see? You would see all the other raisins moving away from you, even though you are not at the center of the expansion. And no matter what raisin you chose to sit on, you would see exactly the same thing. This is what we mean when we say space is expanding. We don't mean that the galaxies, the raisins, are flying through space as resulting from some kind of explosion, but rather the space between the galaxies, the raisin bread dough, is actually expanding. And so what does that have to do with what part of the spectrum we look in? The light emitted by the primeval galaxies is emitted in the ultraviolet part of the spectrum. But as that light travels to us through the expanding space, through that expanding raisin bread dough, its wavelength is stretched from the very short ultraviolet wavelength that the light is emitted at to the much longer infrared wavelengths that the JWST is designed to operate in. So in order to see those primeval galaxies, we have to design an infrared telescope. And that infrared capability is useful for lots and lots of other science that the JWST will do. And so the light that we are all familiar with comes to us in a spectrum of extends from infinitely short wavelength to infinitely long wavelength, from gamma ray to radio waves. And the part that our eyes can see is just a very narrow slice of that spectrum. It's the part that can penetrate the atmosphere and reach the ground. So our eyes have evolved to match that narrow slice. The Hubble Space Telescope is operating on shorter wavelengths of light in the ultraviolet. Our eyes can't see it, but we can be burned by it if we're at the beach too long. The JWST, in contrast, is designed to operate primarily in the infrared part of the spectrum. Our eyes can't see that light either, but our skin can feel it. You hold your hand near a warm radiator or stove burner. When you feel the heat, what's happening is your skin is sensing the infrared light that is being emitted by that warm object. And so that is one of the things that makes the JWST very unique and different from Hubble, is that it is designed as an infrared telescope.
Interesting, Matt. Very interesting. We're going to have to take a quick break right here. We have more questions to ask, but if any of our viewers would have a question, please send us an email. The address, as always, is down at the bottom of your screen. And coming up next with Term of the Month is Stephen.
Thanks, Don. The term of the month is conjunction. Does the mention of the word conjunction make you feel inferior? It's Mercury that should feel inferior since it's between the Sun and the Earth. Mercury has inferior conjunction on September 23rd. First, the easy word. A conjunction is when two objects appear near each other in a sky. In this case, it's Mercury and the Sun. Mercury doesn't cross the face of the Sun. It only does that fairly rarely in an event called a transit. It mostly passes above or below the Sun. Then there is inferior. That means between the Sun and the Earth. An inferior conjunction of Mercury has the Sun, Mercury, and the Earth more or less on a straight line, in that order. A superior conjunction is when a planet is behind the Sun. That can also be Mercury or Venus. And that's the term of the month, conjunction. Back to you, Don.
Thanks, Stephen, and welcome back. We're here talking with Dr. Mathew Greenhouse from NASA about the James Webb Space Telescope. So, Matt, will the images taken by the Webb be better than the ones we've seen from Hubble?
Yeah, the images will be, well, they'll be very different than what is seen from Hubble, largely because the telescope is so much bigger than Hubble. It's more sensitive. It can see a great deal of spatial detail, and it's also an infrared telescope. And so we can take a look at what are the implications of it being an infrared telescope. This is an example, a good example to show that. In the center of this slide, you can see a very famous Hubble Space Telescope image of something called the Eagle Nebula. The spaces between the stars in our galaxy, the so-called interstellar space, is not an empty vacuum. It's filled with giant clouds of molecular gas and dust and molecules. And these giant molecular clouds are the birthplaces of stars. And these big pillars in this HST image are opaque because it's molecular gas mixed with dust. And that's making the clouds opaque and hiding the star formation action that's occurring inside these pillars. But if we look at the same field shown on the right in the infrared, the longer wavelength infrared light can penetrate the dust so that we could peer inside the cloud to see the star forming action in better detail. So the Webb images are different than the Hubble images in that respect. They're infrared images. And the Webb will give humanity its first high definition view of the infrared universe. Shown on the left of this slide is an image from our prior infrared mission called Spitzer. And it's shown alongside an image of the exact same field taken with the Webb, some weeks ago. And you can see immediately the importance of the Webb's ability to see fine detail, angular resolution, as they call it. The giant Webb mirror allows us to see a great deal of detail that the smaller Spitzer mission cannot see. And that's one of the most powerful aspects of the Webb mission.
That's a fascinating image that you have there, Matt, to see the resolution of the James Webb. Now, you mentioned the mirror, and I understand that this mirror is not glass. What material is it, and why did they choose it?
The material is, you're right, it is not glass. The material is made of beryllium. Beryllium is a metal. And the reason we chose beryllium is that as the telescope points in different directions around the sky, there will be temperature gradients that form in the mirror. And so we had to find a material that had what's called a very low coefficient of thermal expansion, so that the shape of the mirror would not change in response to those thermal gradients. And beryllium has that property. It's also very light and stiff, which is important for making anything that flies.
And I understand that it's gold-plated. Why did they do that?
Well, gold is the most reflective substance in the infrared where we're operating. And so for that reason, we chose to coat the mirrors with gold so they could operate as efficiently as possible.
Interesting. Now, how long is the Webb mission scheduled to last?
Well, the formal lifetime of the Webb, the engineering lifetime, is 5 years. However, we expect it to last much, much longer than that. We used very little propellant getting out to the L2 point. So we have lots and lots of propellant on board. We know that propellant will not be the life-limiting component of JWST. It'll be wear out of something else. We'll have to wait and see. But the JWST could last as long as 20 years. We'll have to wait and see.
Interesting. I've noticed in general when NASA sends a mission up, they typically undersell its lifetime. So we're, very happy when it lasts longer than we thought. Now, its sun shield has 5 layers. Why 5? Why not just 1? Wouldn't that have been simpler to do?
Well, 1 would have been simpler, but it wouldn't give us the thermal performance that we need. To make an infrared telescope, the telescope has to be very, very cold. In this case, almost minus 400 degrees Fahrenheit, of 40 or 50 degrees above absolute zero. And the sunshade is what's allowing us to cool the telescope. The telescope will always live in the shadow of its sun shield, which blocks the heat that would impinge on the JWST from the sun, the earth, and the moon. But to block that heat, it has to block it really, really well. This sun shield has an SPF of more than 1 million. So that if you had this thing on the beach, you would be very, very well protected. And to give it that SPF, to give it that thermal performance, we had to build in 5 layers that have a special shape. And each layer is made of a plastic-like material called Kapton that is thinner than a human hair. And each layer is coated with aluminum to give it the thermal performance that we need. The sun shield is about the size of a tennis court, and it was one of the most technically challenging aspects of the mission.
Interesting. Now, where can people find out more information about this amazing instrument?
The Webb mission has an excellent website, and that's what I would recommend people go to. Just Google JWST NASA. You'll come right to our website. And the website will tell you everything that's going on right now. It'll tell you what JWST is going to observe next. There are lots of imagery there and lots of resources there. So that's the one-stop shopping that I would strongly recommend.
Terrific. And how can our viewers get more involved in space exploration?
I want to emphasize that the people that build missions like this come from all walks of life, and they come from all backgrounds. Every kind of engineering discipline is represented in giant projects like this, and all different kinds of science, management, even lawyers are involved in projects like this. And so if you're interested in aerospace as a career, no matter where you come from or what your background is, joining projects like the Webb is a very, very realistic career objective. There's a quote that I like to read. The book of nature lies continuously open before our eyes, but it cannot be understood without first learning to understand the language and characters in which it is written. It is written in mathematical language, and its characters are geometrical figures. That's as true today as it was 400 years ago when Galileo said it. And so to join missions like this and to pursue careers like this, go to college, study whatever you love in college. But if that happens to include science, engineering, and math, apply for a NASA internship and explore doing citizen science at our citizen science website, and take seriously the idea that you can design spaceships like the Webb and have a very rich career in aerospace applied to astronomy, applied to planetary science, a lot of different things.
Sounds interesting, Matt. I want to thank you for being on our program for this month. For our viewers, please visit our website. The address is down at the bottom of your screen. And coming up next to finish out the show is Stephen with What's Up in the Night Sky.
Thanks, Don. What's up in the night sky for September 2022? The days are getting shorter in the north and longer in the south. The equinox is on September 22nd. September starts with a first quarter on the 3rd, full moon on the 10th, last quarter on the 17th, and new moon on the 25th. Venus, shown here on the 1st, goes from Leo to Virgo over the month, rising an hour before sunrise and a half an hour before sunrise by the end of the month. Venus is farthest from the sun on the 4th. Mercury is in Virgo, and the month starts with setting less than an hour after sunset, but rising an hour before sunrise by month's end. Mercury has inferior conjunction on September 23rd. Mars is in Taurus and rises from around midnight at the start of the month to a couple of hours before midnight by the end of the month. Uranus is in Aries and rises a bit before midnight to 2 hours earlier. Jupiter is in Pisces and rises from a couple of hours after sunset to around sunset by the end of the month. Opposition is September 26th, where Jupiter is king of all of the planets all night long. I mean, it's Jupiter. It's always bigger than the rest of the planets combined. Neptune is in Aquarius and up almost all night due to opposition on September 16th. Now, Saturn is shown separately because it's in the other direction. Saturn is in Capricornus and rises before sunset. It's 2 hours earlier at the end of the month, but sunset up north here is also earlier, so not quite 2 hours. Pluto is in Sagittarius and rises before sunset. It's best around 10 p.m. or so, and with a finder chart that goes to at least magnitude 14, and at least a quarter-meter scope, and of course, some patience. The top view of the solar system on the 16th more or less shows how the Sun, Earth, and Neptune line up for Neptune's opposition. Jupiter is close. Jupiter, Saturn, and Neptune are all in the same general direction. And as the planets move faster closer to the Sun, it's easy to see Mercury will soon pass Earth. Venus, the Sun, and Mercury are in the same general direction, though Venus is farther, being on the other side of the Sun. And that's what's up in the night sky for September 2022. Remember, we don't charge money for this show, but we may tax your brain.